Hi, my name is Fred Slane, and I'm the Executive Director of the Space Infrastructure Foundation. Welcome to our course on space standards and architectures. First, let's talk about what the space domain is. There are three essential parts. Of course, the space segment, the thing that makes it unique. The transportation segment, that is launch vehicles, orbit trans vehicles, and so forth. And the ground segment. We're pretty ambitious with the goals for this very short class. There's a lot to explore, a lot to introduce. The overview of the architecture development and related standards for space is pretty important. What standards apply, why you would use them, how it affects your business case, what are the role and dynamics of the standards development organizations, how do they work together or not work together, and then how do you engage in standards, updating them for the next generation of the space industry. It's a lot to cover, and we know it's ambitious. So hang with us and see where we go. Let's take a look at some of the foundational concepts in all of this. Standards are an important component for complex systems in a global market. Fortunately for the space industry, we've neglected this one important component for far too long. It's time to repair that damage and let the industry flourish as it should. A major impact will be in the area of model-based engineering and model-based systems engineering when we have common language for a number of different intricately connected and sometimes not obviously connected pieces. In the future, we're going to have MBSE tools that allow us to do a lot of drop-down selection of standards in some case. And we're going to be able to harvest a requirement set or requirement sets as we build our tool base and reuse a lot of our engineering. As important as those foundational bases for doing this, we want to make sure that you're satisfied in answering the question of why you are taking or viewing this class. You're looking for answers in how to deal with rapid change. You're trying to figure out digitization, multinational growth, a whole number of different things. And there are solutions that are in place that are very well established in many other industries, where an open architecture, or an open framework, is a basis for program structure. So we're sure that in your organization, you have some kind of statement about what it is you do. Standards are a way of calibrating that architecture and allowing you to interoperate with others or other tiers in the supply chain. There are a number of trends that we address, and there are two types primarily: conventional, and there are a number of spending constraints that are going on in the industry from government sources. There's a lot of spaceflight commercialization. There's manned spaceflight commercialization and on-orbit servicing that are all coming to bear. And then there's the whole new space thing with constellations of disposable small sats, a CubeSat market explosion, global competition, components as commodities, and a whole new approach for why we use space, why we build space systems, and how they address market needs. So here's an example of a model. We're going to take a look very quickly at a space project business process model, or BPM. This is a very simple structure put together on a free download tool. And you can see that we've identified swim lanes for the launch provider and the spacecraft provider and the customer and all the different components. Essential pieces of this are the inclusion of contracts between different organizations. Standards, voluntary consensus standards, are enforced by contract. There's no legal requirement necessarily to use them, but contracts between organizations are the medium for identification and then enforcement. There's also some commonality in language and structure that we can see in this business process model that might be useful to go from one project to another. This is part of the area we want to look at in terms of what an architecture and what standards bring to the industry. A pretty common question is, are standards worth the financial investment? Where's the return? The ROI is not realized in 1 year or 2. In this example, the CCSDS File Delivery Protocol, or CFDP, an investment was made upfront for several years, working with a number of different players to build the protocol and publish it. On the first program, they probably spent as much money as they would have spent anyway developing that protocol for a single mission. But because they captured it as a standard, or in CCS language, a recommendation, future missions have been able to harvest that investment and reduce their development costs and overheads substantially. Here's a simple example, but it plays out again and again and again for multiple standards. In addition to reduction of cost, interoperability allows cross-agency sharing on joint programs. An example is ISS. Even if there is not a joint program, the use of common standards for communications, for example, allowed the NASA Deep Space Network in 1995 and 2008 to rescue missions which otherwise may have been lost. So the benefits include mission and joint mission. There are benefits between agencies, governments, and enjoying the services of multiple contractors. Consortium for Execution of Rendezvous and Servicing Operations, or CONFERS, has taken all of this architecture for the structure of standards and the development of open standards to heart for on-orbit servicing and rendezvous. You can see from the mission diagram a rather complete description of the mission area has been established. Concerns of the organization have been identified, highlighting safety and mission assurance. Based on this architecture, a standard out of ISO has been developed and is nearing completion, establishing the principles and practices in language for standards. Future standards areas for collaboration or standards work include space traffic management, or soon to be space traffic coordination, collaboration with the Artemis space interoperability standards development work, and the extension of that ISO standard as the basis for a new technical standard under the AIAA. As a point of full disclosure, the Space Infrastructure Foundation is a member of the CONFERS Secretariat. So what does it mean when we talk about standards development? There are two major points here. One is why your company or organization should get involved in standards development. And the other is that you have to do this well in advance of when you actually need the standard. So there are several bullets here on why your company should be involved in standards development. It's important to note that the Sherman antitrust collaboration rules do not apply in the area of standards development, as industry is collaborating to produce a public document, and the government really does want you to do this and collaborate and participate. Right? It takes a little bit of time to do this, anywhere from 3 to 5 years, depending on the standard. Plan ahead. So let's take a look at what an architecture framework looks like. For the space industry, what we're talking about are spacecraft, launch and reentry spacecraft, and associated infrastructure, for example, ground segment. The major components of an architecture are first addressing the concerns of the body that's working on the problem, and then understanding what all the different viewpoints are of the organizations that are addressing the issue, whether those be operational, systems. There are a number of different ways that things can be looked at. This very simple diagram out of ISO 42010, Systems Engineering Architecture Descriptions, helps us understand what components come together and how to create an architecture or architecture description, the actual instantiation of an architecture from particular viewpoints. First, we start with, on the left, stakeholders. Who are the organizations or individuals who are involved in this activity? What is the purpose? Down at the bottom center. In a space system, this might be the mission. And then what are the particular concerns from the mission that need to be addressed or need to be satisfied for the mission or purpose to be completed? So we put together the stakeholders and the mission statement, and we define what the system is and how it's influenced by the existing environment. All of these things put together help us understand what an architecture is. It's all rather abstract, and so we need architecture descriptions, that is, statements from different viewpoints, and these architecture descriptions would then be views, to understand what our architecture looks like. Some, but not all of these architecture viewpoints are shown here. At the very top level, we have a viewpoint of the enterprise. What is the organization or group of organizations trying to do, and what is their perspective? This could include business strategy, business processes, lines of business, and existing infrastructure. Using the architecture, they can manage change. Systems architecture, then, underneath this, at next level of detail, includes systems themselves and their behaviors. And from these behaviors and systems, we can identify technical standards that are necessary to share information across multiple organizations. We base all of this on systems engineering, well-established processes and understandings that apply across many, many different industries. This information view deals specifically with the launch vehicle spacecraft interface. So you can see that we have a launch vehicle spacecraft interface control document, and we have interface command, telemetry, and mission blocks. So ISO 15863 gives us a standard format for the ICD and types of technical content, but it's not prescriptive. And the CCSDS library provides the language for command, telemetry, and mission communications. What then are the unique concerns of the space industry? Interoperability with other space system objects. While this isn't unique, it is unique in regards to what the space elements are. Building for a sustainable future in space has recently become a major concern of the industry and those who depend on it. And then the ability to perform space missions within space challenges, such as the harsh radiation environment, hostile enclosed environments, isolated systems, distant systems, and at times different gravity potentials to deal with across a mission space. In summary then of our architecture and architecture framework, we're including the space industry with the elements shown in the diagram. We are addressing concerns of the space industry, interoperability, sustainability, mission assurance, for example. We are establishing viewpoints or perspectives of the space industry to include connectivity, operations, engineering, and the enterprise viewpoint. Now that we've taken a look at space architecture and concerns and business case and all those wonderful things, let's take a look at space standards. There are three primary space standards development organizations for space. ISO, the International Organization for Standardization, founded in 1947. CCSDS, the Consultative Committee for Space Data Systems, space agencies of the world, and the American Institute for Aeronautics and Astronautics. The work these organizations do is very foundational, but we are seeing more development in different areas as time goes on and interest grows. There are a number of different organizations, of course, that develop other standards that are very useful. IEEE, for example, for electronics. The Object Management Group for things such as SysML and UML. And there are other SDOs that are relevant. Their work is maturing over time, and a number of different things are coming together. It's a very interesting time to be working in the area of standards, let alone space standards. So let's take a look at what these three organizations do. Here's a little information on their organizational websites, of course, some links for their libraries, the number of standards they've published, what their organizational structure looks like, and I touched on that briefly. So that international body of ISO is composed of national standards bodies and participation by industry. So in the case of the United States, that would be ANSI, the American National Standards Institute. The Russian system, of course, is GOST. CCSDS, space agencies working together, and then the AIAA, which works with professionals who choose to join as members. Here's a quick look at how these organizations overlap. SC14 deals primarily with space systems and operations, CCSDS with space data and information transfer systems. So we can see that common architecture across the two is of benefit, and those two organizations are working together to do that. There are also common areas of interest, such as navigation as a major operational area, but also the structure of information for data messages in that context. The AIAA is a little more focused on US, but it does have an international perspective. And they look, again, at mission architectures and some different launch integration, for example, some different areas, but basically supporting the overlap of the three. With this chart, we give you a little information on how the organizations are structured, both SC14 and CCSDS, under the ISO umbrella. So you can see there are two subcommittees under the same technical committee, and they have different working groups that address different subtopics. If you're interested in more information on these organizations, you should go to the websites that were listed previously. These standards development organizations, with an eye towards the future, are looking towards what mission drivers are in place for future standards. In the past, human spaceflight has been focused on things like space shuttle, advanced to the ISS today. There are future in-space activities, such as commercial space station, human expeditions, human exploration, and asteroids in the future, lunar activities, and so on. So going along this same path, we'll be looking at complex deep space missions, orbital remote sensing, and even the area mentioned earlier, on orbit robotic servicing. Other standard organizations of interest might be such things as the Internet Engineering Task Force and the Internet Research Task Force. Both very much necessary for support for delay-tolerant networking and such things as the solar system internet. ECSS is, of course, working with the European community on standards for that region. As I mentioned, we have the IEEE, we have the Open Geospatial Consortium, and ASTM working specifically in the area of some of the new space tourism kinds of standards. The Object Management Group, as I mentioned earlier, is very well known for UML and SysML, and they have a number of different areas that they work in. XTCE is a very essential component of all the CCSDS work, and those two organizations do, in fact, work together over time. They have future work in a number of different areas, and I invite you to go take a look at what they're doing. Part of the allure or the attraction of an organization such as OMG is that they have a much shorter, faster review cycle. They control their membership, and vendors get to participate through membership and heavily influence those new standards. Just a final note from our section. There are non-English versions of all these standards, or a lot of them, available from the different standards development organizations. I'm going to hand it off to Mike Kearney to talk about communications architecture as one specific area. Thanks for listening. This is a good story. We're telling it through architecture, and we're telling it through standards, but it is the story of space.
Greetings, I'm Mike Kearney from the Space Infrastructure Foundation, and I'll be presenting this summary level class from this point forward. We'll go pretty fast, so if topics seem to jump around, it's because these are cherry-picked charts from our all-day class. We're giving communications architecture a bit more in-depth treatment because of the extensive standardization work that's been done there, and also because joint space missions may have many interfaces, but there's always a communications interface, and it's the most critical interoperability touch point. So CCSDS has developed an end-to-end architecture consisting of 6 technical areas, and we'll walk through those, starting with the Mission Operations and Information Management Services area, or MOIMS, the application layer services basically, followed by Space Internetworking Services, Cross Support Services, Space Link Services, Spacecraft Onboard Interface Services, and the Systems Engineering area, which is cross-cutting topics that wrap around the whole architecture. The significance of the colored lines is the red lines are application layer services from MOIMS that flow end-to-end across the architecture space to ground. The Space Internetworking Services are the pink lines that carry those application layer packets. The cross-support services are the connectivity between the antenna sites and the mission control centers in yellow that allow mission control centers to interoperably work with even partners' antenna sites. The Space Link services are the green lines that flow end-to-end space to ground, spacecraft to antenna sites, and they tunnel through the cross-support services to connect directly to the Mission Control Center application layer services. And the Spacecraft Onboard Interface Services, or SWAS, are the blue lines that provide onboard connectivity between the devices and applications on board. The technical organization of the CCSDS mirrors this architecture, with each area being a technical management area and the bullets underneath each area being the names of working groups that are working on those technical topics. Of course, the CCSDS architecture follows the ISO OSI 7-layer model standard. A layered architecture is critical for comm functions. It prevents lock-in with one implementation and allows technology migration layer by layer. And we all know how fast technology changes in the communication area. We won't explain this model here, but just point out that the key layers that need clean interfaces are the bottom 4: physical, link, network, and transport. And of course, the network management layer talks to all other layers. We've discussed the benefits of a layered architecture, but the best explanation is an example. The Epoxy Dynet mission from JPL was a repurposed spacecraft. They extended their mission to a new phase, went to chase a comet, and in the middle of the flight in deep space, they replaced the flight certified network layer, layer 3, with a delay or disruption tolerant networking DTN layer 3. And because they had clean layer interfaces, they were able to do that. Coincidentally, they had comm outages that DTN compensated for, and it saved the data. Wonderful example of the capabilities and benefits of clean layer interfaces. DTN is really the new standard for the most advanced network layer, specifically tuned to the needs of space. And however, a caveat, some components are still in work, like routing and security. We'll discuss DTN a little bit more on the next chart. Uh, Meanwhile, security across the board is being developed by CCSDS. They're doing it at the link layer. Finally, we have link layer security at the network layer and application layer as well. There's a suite of 8 published standards now and more in development, and it's really important for missions to review and adopt. Also note there are other standards outside of CCSDS that are important security standards, FIPS, ISO, NIST. We discuss them in our longer class. Now, a quick discussion on DTN, delayed tolerant networking or disruption tolerant networking, with the help of an animated slide. We're going to explain DTN technology and how it automates operations when you have disrupted networks. The secret of DTN is that it adds store and forward capability to internetworking. Normal IP networks drop packets in seconds if the router doesn't see a path ahead because one of the links is down. On this graphic, on the vertical axis, we have nodes in the network connected by communication links that are either on connected or off disrupted. And the horizontal axis is time. And so what we see without the DTN capability is that packets that are transmitted will hit a broken link and will be dropped by the routers. And it will retransmit and try again. And in this illustration, there are 3 failed attempts until the 4th attempt finally makes it through because it has a contiguous end-to-end path. With DTN, however, in the same situation, the first packet makes it through because it has the capability to store the link and forward it once the forward path is complete. So we have all 4 packets make it through the network with this shorter latency and higher bandwidth from the equivalent of 4 packets making it. So this would be a great capability for any network, and that's why the IETF is working towards applying this space-developed technology to the terrestrial internet also. Touching on security again, these topics are critical for all missions, especially in this new era of government-sponsored hacking. The starting point for your mission is to ramp up your security awareness by studying the threat analyses and guides from CCSDS, from the very specific cryptographic algorithms and security reference architecture to the more generalized mission planner's guide and standardized terms and definitions. These are highly recommended reading material. They're available from the CCSDS public website for free. And there are also ISO standards besides the ones from CCSDS that are also released as ISO standards. ISO has their own standards, no less than 15 more that are for the OSI systems in general. They're not specialized for spaceflight, but they may very well be applicable to your mission. Just a tip, CCSDS standards are free. The same standards when released by ISO cost money. A short list of topics that are covered in more depth in our full day class, much more layered architecture discussion and tips. The solar system internet. Did you know there was a solar system internet? IP versus DTN, something of a competition, and much more in-depth protocol descriptions and security discussions. So now we're starting on the implementation section of our class, the core of the class, and the first topic is engagement options. You and your company could engage with the SDO, the Standards Development Organization, in any of 3 ways. The first is the average adopter, where you review the already published standards for applicability to your mission, and then you select or adopt what you need. This is lower risk, but you're settling for older technology. But it is less investment by your company in the development of the standards because you don't contribute resources. But unless the solutions that you've chosen are already commercially available products, you still have the issue of development of your system to comply with the standard by yourself. Alternatively, early involvement is when you join an SDO that is already working on a standard that will apply to your mission, that your mission will need. You can get on their mail list, send comments and red lines, and monitor their schedule for completion so that you'll know any risk involved with their schedule slipping and such as that. This provides risk reduction, particularly when it's an emerging technology, and it allows you to manage schedule risk by understanding the schedule for the standard development, as well as the technologies that are being used. It, it adds more eyes on the problem with your colleagues in the SDO. And even more aggressive is very early involvement. You identify new standards that you need, propose them to the SDOs as a new project, and then you stay involved in the standards development. Uh, this basically allows you to capitalize on resources in other companies and agencies who are all putting more eyes on the problem to solve the same questions. Your team can then prototype the standard and evolve that prototype to become the operational standard compliant system. And you can take advantage of other organizations' resources. As we said, more eyes on the problem. Sometimes it seems like there's a bewildering array of the types of standards that standards development organizations produce and their nomenclature for their various types of standards. To solve that problem, SIF introduces a taxonomy of standards, our own convention, which we will shortly map to the terminology used by the standards development organizations. First is technical implementation standards. These are normative, meaning they are full of shall statements, but they have implementable details. You can use those to actually implement a system that complies with them. There are technical reference standards, which are system standards that are normative, though not necessarily directly implementable. They're shall statements, but they may be higher level. They may be reference architectures or other higher level documents. There are best practice standards, which are generally operations and design practices. They're not normative for systems, but if your organization was going to say that you are compliant with a best practice operations procedure, for example, then they would be considered normative for that. There are informative documents which are not normative. They do not have shall statements. They generally provide context and rationale for the prior types of standards that we've explained. And there are hybrids. Of course, there will be some that are mixed practices, documents that have multiple functions from the above list. Basically, not usually a good idea, not good requirements practice, of course. And we'll expand on a couple of key types next. And now some key types of standards. Interoperable technical standards are necessary if you need your program to be interoperable with other agencies, other partners or contractors or companies. Also, if you have multiple contractors and you need your contractors' subsystems to work together interoperably. And a seldom recognized requirement, but is critical, is if you need unplanned contingency support from external organizations. Our little graphic to the right on the XMM Newton mission is a great example. ESA's XMM Newton mission was in trouble. The spacecraft was tumbling. NASA was not part of the original program plan, so they were not configured to support, but their deep space network at JPL was the only communications antenna that could access the spacecraft. So within a matter of hours, because they both complied with the same CCSDS interoperability standards, they were able to lash their communication system together to send a command from ESA through the NASA Deep Space Network to the spacecraft to bring it out of safe mode, stop it from tumbling, basically rescue the spacecraft. So that was a wonderful example of how unplanned contingency support is enabled by technical interoperability standards. And also best practice standards are always great for improving efficiency and performance, basically learning from other people's lessons learned, and by reducing risk because of practices that have been tried and true. An early analysis of all of these standards is critical for your systems engineering team because implementable and interoperable standards have options. They have technical decisions that need to be made before you can implement them, and your systems engineering team has to look at those. Very few can be put on a contract and used as is, but all can be put on a contract quickly if the requirements options are resolved. And of course, as I said before, early involvement with the standards development organization is the best way to accomplish that early analysis. So now back to that bewildering array of standards development organization document types from the space SDOs. On the left-hand column are four main categories: normative and implementable, normative but not implementable, informative, and others. Looking at what the SDOs have, CCSDS has an array of colors of books. AIAA has and ISO have standards that don't discriminate between implementable and non-implementable, and AIAA has recommended practices in some normative categories. There are also guides, technical reports, and other kinds of reports from AIAA and ISO. On the right-hand column is our SIF class nomenclature with best practices and informative documents together, because some of these are sort of a mix of either. So this is the general breakdown of how you map. There's much more detail in the mission applicability guide, which is distributed with our full day class. And now a brief discussion on what standards to choose based on your situation and risk posture. For the least technical risk and the lowest cost, of course, choose those already published and implemented elsewhere, or those with commercially available products ready to go off the shelf. For example, the CCSDS Comlink standards, RF telemetry command, etc., or ECSS Spacewire are good examples. For the greatest cutting edge technical capabilities, but higher associated risk, you could choose those that are in work in standards bodies right now, or just recently published. For example, the CCSDS Unified Space Data Link Protocol, which replaces telemetry and command standards. Did you know about the USLP? Or the CCSDS Solar System Internet with delay-tolerant networking and its associated suite of standards. And the ECSS Space Fiber are all good examples of that. And as we discussed earlier, if you need unplanned contingency comm support, adopt the CCSDS comm standards for comm links. Now to discuss when to choose standards in the context of your project or program schedule. Turns out we can somewhat generalize on that based on the taxonomy of standards, on the types of standards. So we've got here NASA's mission life cycle, phases A through F, and the project management body of knowledge, PMBOK phases, the project management scheme. So more or less mapped to the NASA mission lifecycle phases for discussion, and typical project milestones from SRR to CDR, critical design review, etc. Uh, so the selection of technical reference standards should happen early. These are reference architectures, conceptual frameworks, things that drive broad approaches. So they need to be done early in the mission, pre-phase A and phase A. Design practices are needed before the design starts, so they need to be finished by the preliminary design review for, say, selection of tools for which you're going to be using to develop your design and develop your systems. Technical implementation standards need to be finished by CDR, mid-phase C, and finally, practices, best practices, operational practices, uh, normally would be selected before operational readiness review. But as we all know, many missions have changed their operations concept anytime in the middle of the mission. So technically, you can be reviewing and selecting new best practices like that through the end of your operations phase. The key thing here is that early in your mission life cycle, you need to add to your schedule milestones for selection of these standards of these types. So now to discuss a tool to help you choose standards. This is the Mission Applicability Guide, the MAG, which is a beta test tool that Space Infrastructure has developed that will help prioritize and illuminate which standards are most important for your mission type. We're not going to cover it extensively in this 1 hour class. We distribute the tool to students of our all-day class. And it's extremely customizable. It prioritizes standards by mission type and domain being ground systems, onboard systems, comm systems. So it's basically a spreadsheet. And in the spreadsheet, there are some brown header columns that have the basic data of the standards, titles, and links for 500 plus standards that are all specific standards for space programs from AIAA, ISO, and CCSDS. And the green column headers, there are more than you see here, are the subject of the standard, the domain of the standard, ground systems, flight systems, etc. And the blue header column is mission types, Earth observing, on-orbit servicing, human spaceflight, many more than the blue column headers you see here. And there are scores from 1 to 5 for all of those 500 plus standards. And so if you filter or sort first on, say, comm systems, and second on Earth observing, then what comes to the top is comm system standards for Earth observing missions. So that's the general idea. You'll be able to filter out the irrelevant standards for your mission type. And that's the genesis of this. I've been asked many times in my career from project managers that say, how do we get through this bow wave of a huge number of standards that we have to evaluate for our mission type? And so this was SIF's attempt to try to address that question. This is just the start. Ideally, in the long run, we envision it being online, like a resource that can be accessed by our students, and perhaps even to eventually to the extent of Amazon reviews for space standards. Wouldn't that be great? I said earlier that the implementation section was one of the core pieces of our all-day class. In the short class, we don't have time to discuss standards examples, the mission applicability guide, commercial product options, risks and risks management, Pix Performa and how to use them for your mission, and the guide to the CCSDS colors of books. And this next section normally goes into a discussion of standards by mission type and domain. Basically, using the mission applicability guide, which ones rise to the top for each of these mission types. And however, for this one-day class, we're only going to focus on standards that are important for all missions. But you can browse through this list and see that these are the other mission types that we cover. And if your mission type isn't on that list, let us know. We'll add it. So our recommendation of standards that are important to all missions are architectural standards. As we saw earlier, they're important for the early mission phases. The AIAA plug and play architecture standards is an example, and the security standards in CCSDS and ISO are part of that cross-cutting technologies in architectural overviews, as we already discussed. There are communications and tracking system standards. The basic CCSDS command and telemetry formats, telemetry, command, advanced orbital systems, and US Unified Space Data Link Protocol, USLP. RF and modulation standards, cross support, and space link extension standards for antenna sites are all critical. There are spacecraft onboard standards for in the CCSDS number 850 series, especially electronic data sheets. Everyone should be looking to those as a new area to adopt new technology. The application layer, the navigation standards are key because we're all up there together in Earth orbit, and especially the conjunction data message standard for collision avoidance. When you get a message from the JSPOC saying you're in trouble, you need to be able to read it. XTCE, the XML telemetry and command exchange, is a command and telemetry database standard, also known as recon in some mission domains. And it was an enormous problem for a long time, and XTCE is addressing that. CCSDS voice and motion imagery video for exchange between ground control centers and payload facilities because we're all on the surface together trying to fly our missions. And environmental standards, specifically space debris standards. We all need good actors in Earth orbit that are not going to make the space debris problem any worse. Those standards from ISO SC14 are how you do it. So breaking news is our topic of new important developments in the space standards world, starting with the USLP, the new data link protocol that replaces traditional TMTC and has many advantages over it. DTN, delay tolerant networking or disruption tolerant networking, the next generation of internet style protocols for space. They're the foundation of the solar system internet, which is a consortium of agencies that have agreed that the DTN's bundle protocol is the core foundation for a cooperative, interoperable internet in space. Everyone should be taking a look at that. The architecture and the protocols, bundle protocol and light transmission protocol, have been published, and there are more components in work. The space data link security, finally, security features at the link layer. We've needed that for some time, were recently published. The onboard electronic data sheets, new methods to streamline onboard configuration and control the onboard data systems. Wonderful advancement. The onboard software architectures, there are two architectures that are being proposed to CCSDS for core flight software standards. and one is from NASA and one's from China. So it'll be interesting to see how that comes out. And participation is always welcome in CCSDS for making decisions like that. The ISO Subcommittee 14 has a suite of human techno-medical requirements, which is basically life support requirements and standards for human spaceflight. And ISO document number 24330 is a new document for on-orbit servicing principles and practices for the on-orbit servicing industry. AIAA has a new suite of battery standards and new standards for electromagnetic compatibility. So I've advocated several times that you should get involved in SDOs, Standard Development Organizations, in order to get your mission's needs incorporated into the new emerging standards. For this short class, we'll give you some tips on how to get involved. In our full day class, we SIF instructors offer to help individual students get engaged with contacts and background and technical information for the SDOs that our staff has been engaged with. So for CCSDS, the best way to get started is to go to their public website, ccsds.org, read the public material, including standards in the technology area that you have expertise in. Look at their CWE Collaborative Work Environment page that lists their current working groups. Find the topics, the technical topics that you're interested in. On the CWE page for that working group, you can look at their write-up, find the public documents that they have to confirm your interest. You can email the working group chair and ask to be added to the mail list. Ask him questions, of course, about the technology that they're working in. And you can even ask to be added as a member of the working group with a CWE IDs to get access to the working group files. You should know that for that to happen, CCSDS will ask the lead member agency from your nation for his approval to do that. The meeting schedule is at ccsds.org meetings tab. For AIAA, you should know that even though the first letter of AIAA is American, international participation is encouraged and AIAA membership is not required. So you can go to the AIAA website, review their standards catalog to see if they have technology areas that you're interested in and can contribute to. Look at their list of committees on standards to find the technical area where you want to work and contact the chair there to get engaged. For ISO, Technical Committee 20, Subcommittee 14, at their website, you can view the standards catalog to find interest areas and confirm that they have an area that you want to work in. You can join your National Technical Advisory Group. That is actually a U.S. term. All nations have something that amounts to mirror committees where the participants from SC14 in that committee works their national agendas and comes to consensus at a national level for working in the international SC14 working group. If you have ISO administrative questions, you can contact Nick Tongson, nickT@aiaa.org, and to discuss technical activities or to find your nation's contacts, you can contact Fred Slane at this address. And more contact info to come for Fred, because Fred is going to wrap up the rest of this presentation of our short class. So thanks for listening, and take it away, Fred.
So, in summary, we've looked at space domain and its elements. We've looked at the major and minor space standards development organizations, their scope and relationships. We've looked at the mission drivers, new approaches for how to use the architecture and standards. We've looked at business cases, architectures, and views. Mike gave us a good rundown on communications. And so what we'd like to do is basically reiterate that there is more information available. It's This is a very interesting and involved story through architecture and standards of what the space industry is, what the space industry might be. If you'd like more information about any of the things we presented today, or how to get this course over to your organization, or how to share information, or how to be involved, anything that you can think of, feel free to contact us. Here's my contact information, Space Infrastructure Foundation. Hope to hear from you soon.